Hey, so this is what we've covered. What we know so far is that there's an inverse relationship between the wavelength, right, lambda, and the frequency, which is rho, and that little v basically. And basically, it's saying that if you have a lot of waves in a short period of time, the frequency would be high then, right? But you have to have smaller waves to account for the fact that you're trying to cram more waves in there. And if you have long waves, then the frequency is not as often, doesn't happen as frequently because they're taking up more space. So you have fewer waves per second if they're long, and more waves per second if they're a short wavelength. The other thing is that energy and light are directly related. Energy and I'm sorry, and frequency. So the higher the frequency, the more energy a wave has. So you are familiar, I hope, with that light going into a prism will break down into a rainbow. This is hopefully just something you've become familiar with that you can rate. That's why how rainbows form is they use drops as prisms. But anyway, what Niels Bohr figured out, which was really interesting, is that if you put hydrogen gas into a tube and then run electricity through that tube, he wanted to know, well, if normal light will break into all the colors, what kind of light, what is this going to break up into? So he did that experiment and he focused the light in through a prism. Up here's the prism. And instead of getting an entire rainbow, what he got was just a few lines that pretty much were there and nothing was there. Like here, you can see there's no orange or yellow. There's no that indigo, right? So there's a lot of colors missing from this. And it was curious to him, why would you not get a rainbow? Why would you get just these lines? And so he investigated further and he did some math and all that. And what he figured out was in order for that to be true, and I showed a video of me jumping up and down stairs, there had to be stairs for these electrons to go up and down because when there are no steps, they can jump from here to here or here to there, right? There's any number of jumps that can occur if you're on a hill. But if you're on steps, now all of a sudden you can only jump this far and not anywhere near it, or you can jump that far and not anywhere near it. So he was noticing these as steps. And because of that, he figured out that there's energy levels around the nucleus that electrons can travel through, but they can't just travel Harry carry anywhere. It's not like when you drive somewhere and you can just stop anywhere on the side of the road. You have to stop at these very specific areas that he called energy levels. And these jumps correspond to these exact wavelengths that you're seeing here. So here's the video you can go to watch me jumping up and down trying to explain that further. But the point of all that is that now he started looking at more and more elements, and he saw that every element had this unique fingerprint that allows you to recognize if that element is in whatever it is you're looking at that's being heated up or electrified or whatever. So that was pretty cool, he thought. And because of that, we are able to determine things like how old any sun is. Now, we talked before that every sun is creating every element that we know in the universe. Our sun, if we get out of our atmosphere, so there's no interference and you're just looking through space, our sun emits the signature for hydrogen and it also emits the signature for helium, and that's it. So we know there's only hydrogen and helium on the sun that we have, and other stars emit more of these elements. And so they see more and more, and they know that that star is older than our star. Because as we discussed, you keep adding one to whatever's there until you get through all the elements. So if we're only on number two out of a good 100 and whatever, 120, then of the stable ones, then we're in pretty good shape as far as the age of our star. Okay, so what this led to was a very good model of the atom, which is that there's a nucleus in the middle, and then electrons can occupy these areas around that nucleus called energy shells. And as you might suspect, The smallest of the energy shells can't fit as many as the largest. So the smallest of the energy shells, think about holding hands with someone. If there's only two of you holding hands together, that's a pretty small circle. And if I say, okay, now get six more people in that circle, so it's a total of eight, you would have to spread out your circle and get a little bigger. And then if I said, okay, now you need 18 people in that circle, you'd have to spread out and get bigger, right? So the first shell holds only two. The second shell holds a total of eight. The third shell holds a total of 18, and you will need to know this to fully understand what we're getting into with electrons. So application of that, here's a couple applications. One is if we use this Bohr model of hydrogen, here are the bands that you saw. So notice, right, so hydrogen has like a red and a blue and two purples. Those are all visible. So here, right, you got your red, let's say that's your red, your blue, and then your two purples, right? So this is exactly why we see that, but it also releases some infrared, which is IR, and some ultraviolet. So the kind of thing this is trying to show you is the electron starts where the dot is, and then it jumps down to where the arrow leads. So it starts at the dot and it goes down to the arrow. And every time something like that happens, it releases energy, and that energy is associated with this wavelength. These wavelengths are listed in nanometers, so those are not meters. So if you try to one for one compare it to what we've been using, things like this, right? These are all in meters. So you'd have to do conversion from nanometers to meters for that to work. But anyway, here's a sample question. So what kind of light is emitted when you start at level 3 and then you jump down to the very first step? So you're starting at step 3, you're 3 steps up on the staircase, and then you're jumping down to step 1. So that's this line here. The dot is where the electron starts, and the arrow goes to where it ends. And if you follow that down, that's 103 nanometers. So that's a 103 nanometer jump is what that is. And it won't let me do that in pen. So let me try now. So 103 nanometers, which corresponds to UV light. Okay. And then if you go from 4 to 2, so if we're jumping from 4 to 2, so 4 is here, and 2, nope, those are all going to 1. So 4 is here, and that's going down to 2. So 4 to 2 would be 486 nanometers, or blue light. So that's 486 nanometers, which equals visible light. Okay, so that's one application of this. The other application of this is drawing Bohr diagrams. So using this basis that the first shell holds 2 and the second holds 8 and the third holds 18, we will assume when we're doing Bohr diagrams that everything is neutral. So assume that the atoms are neutral, which is to say no charge. Okay, so no charge. Protons equal electrons. So for lithium, lithium by definition has 3 protons. So we're going to assume neutral. So we're going to go with 3 electrons. Okay. And you're going to put all those protons in the nucleus. And then that first energy level, that first shell, that first ring can hold 2 electrons at most. And after it takes 2 away, it's got 1 left. So that second ring will have 1 electron in it. And that's what lithium would look like. A total of 3 electrons in the 2 shells. Fluorine, by definition, has 9 protons. And therefore, we're going to assume it's neutral, so 9 electrons. So we're going to put the protons all in the center. And then the first shell can hold 2 electrons. And the second shell can hold, we have a 2 from 9 is 7. That second shell can hold 8, so 7 is fine. So you put all 7 that are left in there. 2, 3, 4, 5, 6, 7. There's 7. So that's not beautiful, but it works. And then aluminum. Aluminum has 13 protons on the periodic table. And we're going to go with a neutral atom, so 13 electrons. And we're going to put all our protons in the center again. So all 13 protons go in there. And then that first shell has 2 electrons, and that second shell can hold 8. We're going to need all 8 of those. So that's a total of 10 electrons we put in here. 2 in there and 8 in there is a total of 10, but we have 13. So we have 3 electrons left to put in that outer shell. Is 3 electrons. So in case you're wondering why Heisenberg and Schrodinger investigated this further, basically what Bohr did worked really, really well for hydrogen. He could do math to make the calculations and everything was working out really well. But the problem is it didn't work for anything other than hydrogen. He couldn't predict a lot of these lines he was seeing, like for helium and such. So that's where Schrodinger and Heisenberg came in with their electron cloud model. And that basically shows you where 95% likelihood of finding those electrons. So it's more of a probability cloud of where you're likely to find the electrons. And because it's not as distinct as these orbits that are implied here with Bohr, that's why we call them a cloud as opposed to, and that's more what makes sense is that they would go in sort of a fuzzy way around a cloud. All right. And then we're going to start with the uncertainty principle and talk about that tomorrow.